All right. Hello. Welcome back. We are still in chapter 8, still talking about estimating. Uh, and hopefully you remember what we're doing when you see the prompt to estimate here in AP statistics. When we talk about estimating something, generally we're talking about creating a confidence interval. And hopefully by now you figured out that I'm going to keep asking you what does a confidence interval produce? Range of plausible values, where we think the parameter might lie. So take a moment to remind yourself that confidence intervals give you a range of plausible values. For what? What are we estimating? We're estimating parameters. We're doing that with statistics. So we're generating a range of plausible values for the parameter. It could be parameters. Um, Yeah, and what's the parameter of interest today? Well, mu is the parameter of interest today. What type of data deals with means? We're talking about means here today. This would be, well, quantitative data. Data, has some number that we measured generally or counted. What's the difference between mu and x bar? Hopefully you'll remember that mu is the population mean, and x bar again is the sample mean. And we'll talk about, once again, what does this confidence interval mean? Our point estimate here is going to be our sample mean, our x bar here in the middle. It's always x bar. The critical value here. Notice we've got two cases here. Uh, we've seen this formula for confidence intervals before. Point estimate, where we think our best guess of where it is. Critical value, how many standard deviations we're going to look away. And remember, if we look more standard deviations away, we're more confident. And our standard error is our estimate of the standard deviation based on our sample data. So remember, this is an estimate of your standard deviation. The critical value is how many standard deviations, and the point estimate is our, statistic, the value we get in the middle, or x bar. So we've got two cases here. One is very rare. It's rare for the standard deviation to be known. It's very rare for that to happen. Why do you think that's rare? Why would it be rare? We're estimating the mean. Why would we know the standard deviation if we're estimating the mean? So this is very rare over here. Far more common is going to be population standard deviation is unknown. And this is the formula you're going to use more often than not. X bar plus or minus T star S over square root of N. And your first question should be, what's this T star? Huh? Where'd that come from? Why are we using this T star thing? What is this? Where did it come from? Why are we not using Z star anymore? Turns out, well, we got a problem. If we're estimating sigma with S, notice we've got S here. This is our sample standard deviation. It's not the true standard deviation of the population. That's another estimate. So that's another statistic. X bar is a statistic. S is a statistic. It's from the sample, right? So we need that T star, and that T star is going to account for the fact that we're using a sample standard deviation as our estimate of the population standard deviation. Don't worry about what that means. We'll talk more about it here. So where are we going to find these T star critical values? Again, this is the far more common method. Take a moment to somehow denote that we're going to be doing the thing on the right far more often than we're going to be doing the thing on the left. It is very rare to know sigma. Okay, your critical values T star, those are on your formula sheet. Same place you had been looking for your critical values for Z star. You remember your Z star critical values were down at the bottom at infinity. Our T star critical values are every other value up above this. So if you don't have your formula sheet, pause, get that out. You're going to notice some discrepancies between this formula sheet and the formula sheet in the notes. It's an older formula sheet that I snipped and put in the notes. Your newer formula sheet's actually better and explains more. So that's good for you. Critical values T star. Okay. Once again, we're going to go to table B on our formula sheet. At the very bottom are those percentages. go to the correct degrees of freedom. We'll talk about how we get those degrees of freedom and match the t-star. We're always going to round down if the exact value degrees of freedom is not given. And this is the critical value for the confidence intervals. Okay, so this is where we're going to find it. Degrees of freedom over here. We're going to use these degrees of freedom on the left side and the confidence level C on the bottom. You might notice, if you're looking at this thing, that the confidence levels and the tail probabilities don't match up. You might see on here, somewhere you go down, you find the tail probability 0.25. So it says 0.025. And if we go along with 0.025, we see, what is that? 95%. Well, that doesn't make sense. Yes, it does, because there's another 0.025 over here. So if you're ever wondering, how did we get these T-star and Z-star critical values, it's like a centered 95%. So is what value is T-star? Is that the 95th percentile? Rising inflection tells you no, that's the 97.5th percentile. Think about that. You can verify that on your normal distribution. If you didn't follow the last 45 seconds, don't worry too much. You're not going to have to know this logic about critical value T-stars, but you're going to have to execute on it. So how do we find degrees of freedom? What's the idea here? Degrees of freedom is our sample size minus 1. What's the idea? We're using the T-star, because we're estimating sigma with S. And we need to look a little further away because there's a little more uncertainty. There's uncertainty with our estimate of sigma. So we use those T-stars to account for that extra uncertainty. Because our S is probably off too, right? So our S isn't really sigma, and it's probably small. The hidden thing behind here is that it's probably small. Look at your T-star critical values down here at the bottom. Look at what happens in a column. As your degrees of freedom goes up, look on the left side, degrees of freedom over here, and that's really like n minus 1. If you want to go ahead and write n minus 1 over here, I won't be hurt. And you see, so kind of as our sample size goes up, what happens to our critical values? They get smaller. So as we take a larger sample, we don't have to look as far away. And eventually, it gets to that infinity level. So increasing sample sizes means our estimates of sigma gets better too, but with small sample sizes, they're bad. So we got to look a little further away. And we saw that here as the degrees of freedom increases, the T distribution becomes more normal. So the T distribution approaches the normal distribution as n goes to infinity, because our estimate gets better. So we're going to find some critical values. You don't have to really understand the logic behind T-star critical values. I'll be honest. You do have to be able to find it. So the next thing is a thing you'll see on homework. What is the critical value for T when the sample size is 13 and the confidence level is 95? So A, our sample size is 13. So that means our degrees of freedom is n minus 1 is 12. And our confidence level is 95. So we're looking for T star, 12 degrees of freedom, 95% confidence. That's how I'm going to denote that. Degrees of freedom, confidence level. T star, degrees of freedom, confidence level as a percentage. That's how I'm going to write that typically. So let's find that. We go over here on our T star critical values table. I go down, I find 95% confidence at the bottom. I find 12 degrees of freedom right here, and I find where these two intersect, and I find 2.179 going up from 95 and over from 12, I get 2.179. So that's saying if we wanted to be 95% confident that an interval with size 13 captured the truth, we'd have to look that many standard deviations away. Great. The other one, sample size is 92 and the confidence level is 99%. Well, n there is 92, so degrees of freedom then is n minus 1 is 91, but I got a problem because 91 ain't on the list. So I have to go either 80 or 100. Hopefully you remember from the last page what it said to do, but think in terms of logic. Did we talk to enough people to say we can make an estimate assuming we talked to 100 people? Did we talk to 100 people? Did we talk to 101 people? No. That would be making a better estimate than we are justified in making. We did talk to 80 people, or rather we talked to 81 people, so we're going to round it down to T star 80. And I'm going to make a little note here that we round down if it's not on the T star critical value table. Round down. T star 80 for 99%. We go on our table again, T star 80, 99%. Looks like 2.639. So we can find those hopefully. 63. Great. So we can find T star critical values. Once again, what are these things? These things are how many standard deviations away are we looking? How many standard deviations away are we looking? And where did this come from? S over radical n, or sigma over radical n, back from chapter 7, sampling distributions of sample means. Standard deviation of the sampling distribution of sample means. Okay, so let's do a multiple choice example. And if you're still not good on chapter 7 vocab, you got to go back and look at it. Everything's built on it. Multiple choice example. Recent survey randomly sampled 25 high school students. So I'm going to circle 25. And I'm going to recall that that's, I'm going to write a little n by it. One question asked, how many times do you access social media, Facebook, Instagram per day? Average number reported in the sample was 5.6. What is 5.6? That's x bar. Sample standard deviation of 2.6. So I'm going to write S equals 2.6. And I'm going to circle 90% confidence. My confidence level is 90%. What's a 90% confidence interval for the population mean number of times high school student visits social media sites? Okay, so I see that it's a sample standard deviation. So from the fact that I'm using sample standard deviation, that tells me I'm going to use a t interval. Take a look back at the previous page. We have these two types of intervals, one being a z interval for mu, and one being a t interval for mu. Since we're using a sample standard deviation, another piece of vocab from chapter 7, we're using a t star interval or t interval. Okay. So what is the formula for that? Again, looking on that last page, it's x bar plus or minus t star n minus 1 degrees of freedom s over radical n. So I need to figure out which one of these formulas matches up with that. Right away, I see it's going to be radical 25 in the denominator. So I can get rid of b and c right away. And now it's between a, d, and e. And it looks like it's up to the t star critical value. Let's find the t star critical value for 24, 90% confidence. How do I get 24? That's n minus 1. We go over here, 24, 90% confidence. Looks like 1.711. 1.711. Got to be answer D. Okay. So we can use t-star critical values. That's a really common question where you got like 3 different pairs of answers, and you got to use kind of your ACT knowledge, narrow it down, find which one we're talking about. So we can find intervals in multiple choice settings. We can find critical values. Sometimes we're going to have to just kind of find the interval from nothing. So here we talk about T star and Z star. It talks about where this T star interval came from. You can read through this. It's kind of, fun background. And it's prep for the next unit. But the idea is this t-test came about because we saw that when we take a sample standard deviation and use that as our estimate for sigma, we get really big standardized values sometimes. We get values that are way too many standard deviations away, it seems. Why is that? Because our estimate of the standard deviation is too small. Extraneous, don't worry about it too much. Down the bottom here, on the next thing, AP note, take a look at your formula sheet real quick. Because, well, this is kind of weird. This is kind of weird because they've added something to your formula sheet, and I'd like you to notice that. Sampling distribution for means. Here we have our mean and our standard deviation of x bar, but now they have something called S of x bar. That's the standard error of the sample statistic. And I'd like us to add that here, standard error. So this is our estimate of the standard deviation, is this standard error, and it has data that comes from the sample. So that's either S over radical n or square root p hat 1 minus p hat over radical over n. And what's the idea behind these? Well, these are the best estimate we can do for the standard deviation of these sampling distributions. Uses sample data. Sometimes it's off. So we have this thing called the standard error. It gives you a definition for it, an interpretation of it. In repeated sampling of the same size, the average distance between the sample means and the true population mean will be the value of the standard error. Again, that's an idea. Go back to chapter 2 for your template for standard deviations. On average, the value is this far away from the true value. I'm talking about, what is a standard deviation? True for the population. The standard error is the estimate from the sample. Cool. So let's get moving. We have a study of commuting times, reports travel times to work of a random sample of 20 employed adults in New York State. I'm gonna circle 20, put a little n by it. The standard deviation of the sample is SX equals 21.88 minutes. What is the standard error of the mean? Interpret this value in context. So standard error of x bar, so I'd write that, is from your formula sheet right here, S over radical n. That's going to be 21.88 over radical 20. Putting that in your calculator real quick. We get 4.89. What does that mean? On average, the sample mean travel time will be 4.89 minutes from the true mean travel time. I'll read that again because my handwriting's sloppy sometimes. On average, the sample mean travel time will be 4.89 minutes from the true mean travel time. That's just an interpretation of this estimate of the standard deviation of x bar. What are we talking about, guys? That's stuff from chapter 7. Take a look back at your, if you don't have that chapter 7 picture I let you use on the test, print it out, get it, look at it, because everything's on there. If you don't know the names of all those things, ooh, we're in trouble. So let's keep moving. Now I'm going to finally give you the calculator stuff, because in practice, we're going to do most of these in the calculator most all the time. And this first thing is the Z interval, and I don't know that we're ever actually going to do this. This is exceedingly rare. In fact, I don't even think we're going to do an example in the notes right now of this, because it just doesn't happen. Because why is it exceedingly rare? Because you have to unknown mu and known sigma. Well, when does that happen? When do you know the mean of a distribution, but you don't know, don't know the mean, but you do know the standard deviation? And why is that an issue? Because the mean is in the formula for the standard deviation. I don't know. I got problems with that. So it's not going to happen very often. It's very rare. It's got a how to do it in your calculator here if you want to read through it. What we are going to do, however, very commonly is the t-interval, and sometimes it's called a one sample t-interval for mu. How many samples was it? What's the critical value? What's the statistic we're using to estimate it? And what are we estimating? So the t-interval, where is it? It's, what is it? Stat, tests, t-interval. What do we put in? It's pretty easy. You tell them, do you have the data, or are you going to put in statistics? Really, if you have the statistics, only 3 things you're putting in. What is your X bar? What is your standard deviation from your sample? What is the sample size? Sorry, one more thing. And what is your confidence level? I would tend to write those 4 things down in the do step. They're probably written in the problem somewhere, so it's not a big deal. And then it gives you an interval, and you interpret it. Guys, creating the confidence intervals, that's 1 out of 4 points here. You got to know, what are the words we're using? What justifies the use of this procedure? All that. So we're still doing random, normal, independent. You'll still have those conditions. When to use, please note, you need, well, never mind. We'll talk more about that later. So when we do, it's down below. I got ahead of myself. So multiple choice example. Let's knock that out real quick. Let's do this in our calculator. So pause, try and put this in your calculator. Go find your calculator if you don't have it. Let's do this real quick. Determine the mean cost of groceries in a certain city. Identical grocery basket of foods purchased at each store in a random sample of 10 stores. Great. Average cost is $47.52. Standard deviation of 1.59. Find a 98% confidence interval. Let's write down some numbers down. X bar is 47.52. Standard deviation is $1.59. The sample size is 10. The confidence level was 98%. So let's put this in our calculators and find the interval. We go to stat. We go over to tests. We're doing not a t-test, but a t-interval. That's option 8 there. We have the statistics, so we're going to put that in: 47.52, 1.59, 10.98. And it makes it for us, hopefully. There we go. 46.1 to 48.9. 46.10 to 48.94. Well, poop. That's not how our intervals are presented. So we know it's 47.52 in the middle. Let's do a little subtraction. So we do 48.94. We subtract away that mean of what? 47.52. We see we must be going plus or minus 1.42. So that's answer option D. So we can find intervals. We can do the quick stuff. All this setup is really to do 4-step process sorts of problems. So now it's time to do the state, plan, do, and conclude. Again, state what test you're using, state what parameter you're estimating. Define the, I guess that goes to here. Check the conditions. That's a plan step. Write out your interval and simplify your interval. That's the do step. Interpret. That's the conclude step. So we have these 4 steps. State, plan, do, conclude. Looks a lot like what we've been doing previously. Let's do one. What's nice here? Manufacture high-res video terminals must control the tension of the mesh. Oh man, doesn't this sound like fun? That lies behind the surface of the screen. Too much tension will tear the mesh. Too little will allow wrinkles. Okay, tension is measured with an electrical device. Some variation is inherent. Okay, the machine doesn't work the same every time. Here are the tension readings from a random sample of 20 screens. Construction and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. Okay, so what we're gonna have to do, state plan do conclude, the major difference between this and the previous unit when we were estimating proportions is that instead of successes and failures being at least 10, now we either need a sample size that's large enough, or we need there to be no outliers or skewness, and we can construct a quick graph to make an assessment of that. So go back, highlight those things. We can either have an assumed large sample size, n greater than or equal 30 lets us get away with the central limit theorem, or we're going to need to make a graph, and we're going to need to make a graph. So let's do it. Manufacture here. We're going to put some data in our calculator. So first thing you need to do, I'm not going to sit here and do it for the video. Pause the video and put all that data in list 1. Go to stat, hit edit. I'll show that again. Stat, edit, and we're going to put all that data in list 1. Pause and do that because you don't want to watch me do that, and I don't want to take a minute having you do that. All right, that was very exciting. So hopefully you've put those 20 data points in. We're going to need that later. So let's get to doing it here. We're going to construct a 90% confidence interval with the mean tension mu of all the screens produced. So the first thing we're going to do is we're going to state. We're going to say mu mean tension of all screens produced on the day, whatever day this happens to be, whatever. Our plan, we're going to construct a 90% confidence interval for mu, and we're going to use a 1 sample t interval for mu. It's the name of the procedure we're going to use. So we're always going to, in the state step, we're going to talk about what's the thing we're estimating. In the plan step, we're going to say what's the name of the procedure we're going to use to perform that estimation, and then we're going to justify those conditions. We were told that we took a random sample. We need independence. Well, let's do normal. We'll do independence next. Independence. How do we get independence? At least 10n, that is 200 screens produced. And we'll have normal down at the bottom. And let's go ahead and, well, how can we justify normality? How can we justify normality? So how do we do that? Well, let's take a look at the data. Let's take a look at the data. We'll go second stat plot. I'm going to turn plot 1 on. Let's turn it on. And we're going to go down here. Let's look at a little box and whisker plot of that data. Let's see, does it look skewed? So we'll go ahead and do that. Second y equals pulls up, a zoom. We're going to go to, what is it? Zoom stat is number 9. I don't know, that looks pretty symmetrical to me. Let's hit trace. Let's trace. Let's plot that out. 233, 275, 308. All right, so let's make a little graph. The data from sample is symmetric. And then let's draw this thing out here. All right, 233.5. 275, 308.85, 337.45, and 374.6. All right, so you'll see that most of our work is in the first 2 steps. Most of the work's actually in the second step. So we've planned. Now the do step is going to be quick. Well, I'm not going to need very much room at all for the do step. because the do step is just like, what's the numbers the calculator gives you real quick. So let's go ahead and do that in our calculator. Second quit, stat, go over to tests. We're going to go down to t interval, hit that t interval. We're going to use the data though this time. We're going to use t interval and data. We're going to use the data because we've got the data. We put it in list one. We don't have to calculate a mean and standard deviation. The calculator will do that for us. The only thing we need to change is the C level. We need to change that to 0.9. We do that, and it gives us our interval, 292.3 to 320.3, 292.32 to 320.32. That's all that the do step needs to contain. Seriously, you've put the data in your calculator. Conclude. Go ahead and look at your template. We are 95% confident, 90% confident that the true mean tension is captured by the interval 292.32 to 320.32. All right, so we can create an interval, and the two sample case is like the same, just looks the same. So that's what the process looks like. Let me zoom out again. I'll be scanning these and putting these in for your notes. Easy times. Choosing a sample size, I might skip these examples. I'll probably do one. Your margin of error calculations are going to look the same. To have a desired margin of error calculation, we're going to be solving that equation occasionally for n. Hopefully you can do that. Where did that come from? That came from x bar plus or minus z star sigma over radical n. That's the margin of error part. It's the backside of that formula. We may occasionally have to use that. Let's do one on the next page. Calculate a little sample size here. Example, how many monkeys? I want to estimate how many monkeys it's going to take. Estimate the mean cholesterol level mu. They would like their estimate to be within 1 milligram per deciliter, 95% confidence. Previous study suggests that the standard deviation is 5. So we've got margin of error, we want to be 1. Confidence level is 95%. Sigma is 5. So we need to solve z star sigma over radical n. That has to be less than or equal to 1. 95% confidence, that's 1.96. Sigma is 5 over square root of n less than or equal to 1. Solving for square root of n, you're going to get square root of n greater than equal 1.96 times 5. I'm going to put divided by 1 here. It looks goofy, but just to keep, that'll make sense when you look at homework. Square both sides, you get 1.96 squared. 5 squared over 1, and we get that to be 1.96 squared times 25 is 96.04. So n has to be at least 96.04, so that has to be at least 97 monkeys. You need to be able to do that kind of algebra to solve for a sample size. Again, told you day one of the class, the hardest algebra you're going to have to do. Solving for an n that's inside a radical. So, exciting times. Cool. I think the next example, the matched pairs example, I'm going to talk about, but I'm not going to do. When there's two samples taken, we might be interested in the difference, and that might be a before and an after, and you could make that difference to make it a one sample test. I'll tell you on the next example. You're going to construct a 95% confidence interval for the mean difference. We'll hold that in the bag. Don't worry about that too much. So sometimes it might look like there's two sets of data, but if it was taken in one sample and you need to take a before and an after, then it becomes a one sample test. I want to look at one thing real quick, one example, comparing two means. That would be a mu1 minus a mu2 sort of a situation. saying, is this mean greater than that mean? How much greater is this mean than that mean? What if I wanted to estimate how much greater the mean, car cost at Park Hill South is compared to the mean park cost at Park Hill? I don't know. Maybe that's something interesting. Two sample t interval for mu1 minus mu2. It looks the freaking same. We have the same conditions. They're double the conditions. And we have a similar looking interval. I'll write it a little larger here. X bar 1 minus X bar 2 plus or minus T star square root S1 squared over N1 plus S2 squared over N2. So I just want to do one example with you real quick, fire stations example. Let's take a look. One or two fire stations in a certain town responds to calls in the northern half of town, and the other fire station responds to calls in the southern half of town. Great. One of the council members believes that the two fire stations have different mean response times. Let's circle that word, different mean response times. He believes that. Response time is measured by the difference between the time an emergency call comes in and the time the first fire truck arrives at the scene. Data were collected. 50 calls from the north, mean of 4.3, standard deviation 3.7. So north, N is 50, X bar is 4.3, S1, I'm going to put ones on all these, is 3.7. And we'll have similar data for the south. N sub 2 is 50. Mean of 5.3, standard deviation of 3.2. X bar is 5.3. S2 is 3.2. So that's, oh, we can't see that. That data right there out to the side. So sometimes it's nice to summarize all that. You start circling all those numbers and maybe it gets confusing. I like tables. I like tables. Don't you like tables? Make tables. A, construct and interpret a 95% confidence interval for the difference in mean response times between the two fire stations. So let's go ahead and state plan, do, conclude, and we're done with that. We're done with the video. This video is too long. I know it, you know it. I'll leave a couple examples for in person. So let's get started. So state, we'll say mu sub 1 is mean response time for the north station. And mu sub 2 will be the mean response time for the south station. Great. Fantastic. And we'll plan. We're going to do a construct a what are we doing? 95% CI for mu1 minus mu2. We're going to do that using a 2 sample T interval for mu1 minus mu2. And we need to check conditions for that: random, normal, and independent. Random, we were told that we took a random sample. Normal, well, both our sample sizes, N1 and N2, those were 50, which is greater than or equal to 30. So the central limit theorem kicks in. And independent, what does a call in the north have to do with a call in the south? They should be calls selected independently and at least 10N, that is 500 calls. All right, so we've stated, we've planned. Now we go ahead and do, but you're at this point, we're saying, man, the do step's the easy step. We just type stuff in our calculator. Yes, you do. So go ahead and go stat, turn this thing on. Stat test, we're going to do a 2 sample T interval. How many samples is it? Is it a Z or a T statistic? What's the thing we're estimating? 2 sample T interval for mu1 minus mu2. We have the stats in this case, so let's go ahead and put the stats in. I wrote the stats up here. X bar 1 is 4.3, 3.7, 50, 5.3, 3.2, 50. Confidence level 0.95. Pooled, we're always going to say no to pooled. Calculate that thing. Great. Negative 2.37 to positive 0.37. All right, state, plan, do. Do step doesn't need much, guys. Conclude. We are 95% confident. The true difference in mean response time, north minus south, is captured by the interval negative 2.37 to positive 0.37. Okay. And then part B asks us, does the confidence interval support the member's belief that the two fire stations have different mean response times? Explain. I don't know. If they weren't different, what would the difference be? 0. Is 0 a plausible value? Yes, 0 is in the interval. B, since the interval contains 0, 0 is a plausible value. So they could have the same mean response time. All right. Longer than I wanted. Chapter 8 and 9 videos are going to be longer than you want. Sorry. That's it. That's the content. We'll go back and do some of the notes I skipped tomorrow in a video. Next week, have the reviews done by next week. We'll be looking at reviews and FRQ practice next week, and the week following is your exam. If you're watching this in person for second semester, I'm sorry, I don't mean anything. So, see ya.